I'm dedicated to create the last video on charge to mass ratio, which will get us closer to the elusive electron. In the last video, I went through some equations. Some of them I didn't understand. I think now I understand them. So let me go through some of the basics. In order to create this circular pattern in that one tube that we saw on one of the videos, we have to go through two plates. We have to go through a negative plate that actually is boiling off the electrons with a heater, and then a positive electron, which is called the anode, which accelerates that electron. So first we have an increase in energy. There's two ways to express this energy. One is through the fact that each one of these is two, there's a potential difference between these. Just like dropping a ball from the sky, the potential energy is high and then it starts going down and becomes kinetic energy. In the same way here, between these two plates, we have a difference of voltage, in this case about 200 volts, and that electron picks up energy by going through those. So one way we can express that energy is electron volts. So we're actually using the voltage potential difference to express that energy. Another way of expressing that energy is the classical 1/2 mv squared, where the m is the mass of the electron and the v squared is the velocity of the electron squared. We had that pickup of energy, so we've got this energy change. That gives us the velocity of that electron. We're going from electron volts, and then that's going to give us the velocity of that. Once we have the velocity, we have this magnetic field that pulls that electron in towards the center, just like it's orbiting the center of that. And that center force is magnetic force. The magnetic force is going to be given by the electron times the velocity times the magnetic field. So if we know what the magnetic field is and we know the velocity of the electron, then that can give us what that force is that's pulling it in, and then we can figure out what the charge to mass ratio of this whole thing is. Now, I need to write on the board next, and I'm going to create my first whiteboard equation setup here. So that's where I'm going to go next, and hopefully you can follow the steps. I'm going to go slowly because I'm not that quick anyway. So stay tuned, and I'll give you some
Okay, I'm
writing
back.
on the board.
Let's see what we've got here. We've got 1/2 mv squared, which is the kinetic energy of our electron, where m is the mass of the electron. Here's electron times this voltage at the anode. That is that's the energy that the electron picks up doing that way. Here's the force on the electron as it's doing that circular thing with the magnetic field that's deflecting it. So we have E, which is the charge of the electron, times the velocity of the electron, times the magnetic field. So if we know the magnetic field, then this will help us get to our final result here. The A that I have written here is for the acceleration. Well, it's just acceleration, which is the change in velocity over time. And that is when you're going around in a circle, that's v squared over r. V squared over r gives you the acceleration of that uh, body, even though the velocity stays the same. The fact that we're going in a radius, that gives us an acceleration of that velocity. Then let's see, here's force equals mass times acceleration. That is Newton's basic law. Force equals mass times acceleration. Now let's see if we can start putting some of these pieces together. Well, one thing is we can, let's see, where do we go next? It should be easy, but let's see what I'm headed towards. Okay, the force equals mass times acceleration. So I can put this EVB as the force. There's the E. I got to select my marker there. That is the E is the electron. The V is the velocity of the electron. And B is the magnetic field. And force equals mass times acceleration, then that means mass times the v squared over r. Let's see if I can put parentheses around that to make it look pretty. Okay, I'm doing better than I expected. Anyway, that is the force equals mass times acceleration. Now, the thing that we're going for is what is the charge to mass ratio? The charge of the electron, which we don't know, and which J.J. Thomson didn't know, and the mass of the electron, which he doesn't know. But he can find this charge to mass ratio. Let's see if we can jiggle stuff around here and make that look right. Well, we can divide both sides by m, then we'd have E. Oh, here, let me get the eraser. I knew that was going to be needed. Get the eraser and erase that out there. Go back to the marker. Getting better with this. E divided by M. Divided the M out over here. And then what does that leave us on the right-hand side? Well, if we divide both sides by, well, let's just do it in slow steps. I told you we'd take our time, so let's just go ahead and do that. V squared over R. And then if I divide both sides by the velocity of the electron and the magnetic field, that's going to give me V squared, the numerator, and then V, same velocity, times the magnetic field. Okay, so far so good. Then let's see, what does that leave us? Well, I'm going to go up here and do some tricks with this thing, because what I want to do is put this in terms of the voltage on the anode, the accelerating voltage at the anode, and get the velocity out of here and put it in terms of this voltage, which we know at the beginning. So let's see what we get here. If we look at V squared, going over to this one, equals, now let's see if I don't want to go too fast for you. Let's see, we're going from this one down to this one. And let's see, if I multiply both sides times 2, that will give me 2 EVA, and then that'll be divided by M. Let's see if that made sense. I divided by M, so there's V squared. Now here's where I'm headed is, I'm trying to plug in V squared down here. Let's see what we get with that. V squared, let's see if this makes sense. Maybe it will, maybe it won't. plug in V squared here. This isn't working quite the way I thought it was going to be. 2 over m. I'm just following the rules of algebra, so this should work out. Let's see, if I plug in for V squared, that's going to equal 2 EVA. And then in the denominator, it's going to be V. This isn't so easy when I have to actually challenge myself to do this correctly. That V and B. Let's see, what is V squared over R? Oh, I should have canceled out the V here. Should have canceled out the V. Thank goodness for an eraser. Let me come back down here and don't go so fast. Okay, let me get my marker going again. So I'm going to cancel the V out, so that'll be V over B. You buy that? Where'd the R go? Where'd the R go in all this? Somehow the R disappeared. Oh, okay, we got to have an R down here. And there was an R here. All right. Now I think we've got things going right. Now, back to this V squared thing. Well, I don't have V squared anymore. So here's what I'm going to do to make this all work out. I can replace the V squared with something. So what I'm going to do is square both sides of this. Square the E over M and the V. And I'm going to make that E squared over M squared equals V squared over R squared B squared. Well, we still got that V there, that pesky V. But I've got this, let's see if I can do my cursor there. If we got that V squared, we can plug that in for this thing. Let's see what happens then. Then I've got E squared over M squared equals, now I'm going to get rid of this V thing here. I'm going to replace that with 2EVA over M R squared B squared. Looks like a mess, doesn't it? But I've got an extra E on this side, so I can cancel this E out and take that into just a single E. I've got this M here, get rid of that one. Then I can just make that a single M. So now I have the final result that I wanted to achieve, which is charge to mass ratio equals 2 VA, that's my accelerating potential, over R squared. That's the radius of that electron spinning around, and then the magnetic field. So, if you remember way back when, I said something about trying to see the atom. Well, this is the first step that we get, is to get the charge to mass ratio. And these are the values in the experiment that we can use. We've got the accelerating potential voltage, It's about 200 volts. The radius, which I don't know from that diagram that we looked at or that picture we looked at, what was spinning in that Teltron tube, and then the magnetic field, which that can be determined. So I can plug all these numbers in, then I get the mass to charge ratio, which makes me very happy. And to show that I'm very happy, let me put some teeth in here. That is about the worst drawing I have ever seen. Anyway, this was the result that we wanted. Because this are values that come from that experimental device, then we can get the charge to mass ratio from that. Now, what kind of numbers can we actually plug in here? What would the magnetic field be? What would the radius be? Well, let me come up with those values from the experiment, and then we'll plug them in and see what kind of value we get for charge to mass ratio.